Good afternoon. My name is Thomas Weber. I'm happy to present you my presentation, which I'm going to do this together with my son, Tobias Weber, who just started to work with Mathematica, but helped me in this whole presentation. A few words about myself. I'm a Mathematica user from version 1.2. I used it to make my PhD during the time of the PhD for studying economics, and I'm working since I finished my PhD at the banking industry, and we do all kind of modeling, quantitative questions, and very often Mathematica is the background for doing kind of analysis in this environment. So environment is mainly pricing, derivatives, or risk management. And I used to have some employees. Everybody had to know Mathematica, but we were not selling Mathematica skills. We tried that. We were not able to sell in Germany, at least where we come from, Mathematica skills. You have to sell solutions. And we found that using Mathematica, we are very capable of doing some kind of solutions where other companies had big problems. Like, for example, we were consulting one of the major banks in Germany for the first time when they tried to do value at risk. It was a Mathematica notebook where we developed the first value at risk calculation. Same when we did calculation of credit exposure, when you try to find out what you can lose in the future, and you have to simulate stuff, and that was also done in Mathematica. So we like to do prototyping in Mathematica. We always built throwaway prototypes. We only had one occasion in over the 20 years I'm working in this industry where actually one Mathematica application got into production for half a year. Then it got thrown out because IT department said, no, it's strange software that doesn't fit in our architecture, so it was thrown out, which was nice for us because we first made the prototype it was a smaller project, estimation of the term structure. We were done in 4 weeks about that. It worked to everybody was happy. Then we had the chance to do the implementation in C++, which took a year. So out of this small project, we had a big project putting this into software. So, okay, so much to my person. So I like to do, I'm interested in biking. It's fun to ride my bicycle, and this is now some hobby work, but from the setup, how we do that, I think it's very comparable how we work in banks. So we have a lot of data. We have to find a model to describe this data or work with this data and see, and we don't know at the end if this works out or it doesn't work out, if we have to improve our model, or how this works. So I think the setup is very similar to the way we work in banks, and from that point, it might also be interesting if you're not so much in bike riding. It's just if you just want to know how we use Mathematica in practice. Okay, and I'm not used to this presentator software. We always use the traditional notebook. Okay, what's the setup? There's a by Grace from Belgium. I just learned this. From Belgium down to Greece. And the challenge is rather simple: be as fast as possible, start in Belgium together. We start all together, or everybody starts together, and you have to go to Greece as fast as possible. Very simple setup. The only thing you have to do, you have to meet certain checkpoints. So you have to go here in the Alps, then over the Alps to Slovenia, then from Slovenia to Poland, and then you can go down to Greece. So it's a longer distance. And what's unique about that is that there's no predefined route. So one of the challenges that you get the tour, or at least the checkpoints in November, and I promise you, you're busy until the start of the race to find out what the best route is. Okay, now that was a challenge, and when you start out, what do? You go to the available software like my right or whatever its name, and try it out and try the best routes. First of all, most of the routes are very similar, but there are abbreviations between the routes. So find what's the best route? How do you evaluate it? That's at least the moment when you think about, well, we have this wonderful tool, Mathematica, where we can maybe do some kind of analysis. It's not a simple problem because the data is not very good structured, but well, let's try to see how far we get. Okay. What's also important, if you do this kind of ride, and this is a picture from the last year's ride, well, you start here and you end up here, and you see how everybody goes over the course over Europe, and everybody is equipped with a tracker, which sends your position to the satellite. It's get captured, and you can see it then on the web page. Actually, you can download, if you know where it is, you can download this data. So actually, we have collected all the data from all this year series, the previous race, to find out which kind of tour they did and how they, how fast they were, and everything. So we have a situation where we do have a lot of data available. And I want to show you, just to give you an idea. Give you an idea how this looks like. We look at the second stage where we start in the Alps and go to the over here to the target in Slovenia. And I just picked 4 riders, and you see them with the different colors. And now we have a night situation. Everybody goes to sleep. That's kind of when we have the triangle. Then you see the one guy, the American guy, he really gets up 1 o'clock in the morning to start. And we go all here. Well, almost everybody on the same route. There are not so much routes through the Alps, but then happens something strange. You look at this guy, he's from England. They always have their special way. And he's much faster than I, or than we. So what happened here? He did choose the better route. So my preparation, half a year work on preparing didn't find that kind of route. So I was not happy about that. And we continued to work on that. But first of all, some other things. We have in Mathematica travel directions, which allows you to travel from one place, to find a route from one place to another place. Great, because you have this in Mathematica, there's a lot of, you can use it in Mathematica in this environment. So, great. But the problem is, if you look at the data which it connects, you see it's just a straight line, more or less, of the speed. It doesn't take into account if you go a mountain up or down. So, not insufficient, very insufficient. And what I don't like about this at all is there's nothing you can play around with. So it's not sufficient to do really planning. That's the kind of tour they find. So that's the tour the other one guy used. For example, and this is the one provided by Mathematica, so it does find something, but it doesn't take into account any of the problems. So what do? Well, build your own. So we started out building our own. And to do that, we retrieved data from OpenStreetMap data, OpenStreetMap. And okay, that's in German now at the moment, but you have this accessible as well in English. And so and there's a nice notebook about how to do that, where we got inspired from looking at that. And you can download data for the region. One of the problems is, well, here we show how you can find out what kind of region you want to download. If you download that, that's megabyte of data, which is huge amount of data. And because in this data, everything is in this data, you do see almost every building. So when I saw this presentation this morning where he randomly did some locations to find out how the storm affects. Well, that's all data available. The only problem is it's big and it's hardly accessible. My Mathematica crashed if I try to read it in, and it will never come to end. Okay, we did this anyway and started to build the network. The data consists of nodes, ways, and relations. We are interested in the ways, and we need the nodes because they are connected by ways. And we can just extract that from the data. And this works if you reduce your data set very much. Okay, so that's what we have done here. So you see the nodes, the ways and the nodes, how they look like. We have geoposition. And then you can build graphs out of that. And that's a graph between the tour from Cillian to Hamburg, the one where you have seen the one guy going other directions. And we were happy coming up with this beautiful picture. Hope you enjoy it as well as I do. The problem is it did work. What we are not really what is missing basically is to weight the tours we are taking. So we want to get the hills in. So that's a challenge, and the data is not available in OpenStreetMap. So it's a shortcut, but we are not, so we didn't get to the end. Another problem, we were not really able to work with these CAFs of this size in Mathematica. Just too big. And another issue is that the numbering has to be in a certain way that you can really work with that. If you just take the nodes, it doesn't work. So what do next? As I said, not an unusual situation in a project at a bank because you always run into some area and it doesn't, in one-way streets and you have to turn around. But there's help. Actually, there's at GitHub, there's a project which allows you to do OpenStreet routing, routing on top of OpenStreetMap, which is actually used by one of the, this is a joint venture, if you want to name it like that, from one of the main provider of routing engines. So wonderful, and it's in C++. And that's a situation, at least in banks, where we always are quite happy if we have something in C++ because we are able to integrate something in C++ within Mathematica within minutes. Why? Well, we have worked with Mathematica for 20 years. We have built up a wrapper for the MathLink, and we have built an environment where we can just more or less say, this is the class we want to integrate, and then we do have it available. So actually, we most of that have it available. And we asked them, and actually they did provide us 2 routes. Also the route from the English guy here, when we did, maybe a little bit down. So what we have done here, a little bit down. Actually, you can, no, down. You can put this up as a local server. You can download, compile it, have it available as a local server, which is also very comfortable because allows you to do some kind of stuff like that in trains in Germany where you don't have access to the internet. So you can work with that. And then you get back the waypoints and stuff like that. And you can just read it in Mathematica as a JSON file, and you have the data available. So it's a really convenient way, this way, to have it as a server, but we also integrated it as a C++ routine in Mathematica, extended Mathematica, so that we can really work in details, find out how this works. And as I said, it does shows you. And yeah, so here at least you see the root, and you see why Mathematica didn't use it, because using the geo elevation data from Mathematica, we colored where the mountains are. So here there's a mountain. That's the reason you circumvent that region. So if you're a bad climber, then take the other route. But if you're a good climber, then that's a shorter route. And actually faster route depending on your climbing abilities. There's more to it. What we like here with this open street routing machine is that you can define all details, how, for example, the surface affects your speed. So there's so we can overwrite this file simply, and then we can try to find out how we might change the settings to see that we try to get the setting right. Okay, just here, that's what we made available. That's our executable based on MathLink, and we all have this functionality now available to do further planning. And that's, as I said, in our environment, a simple thing to do. Okay.
So in the next step, the idea, or what we wanted to do is we wanted to estimate and analyze the data we collected from previous tracks, and also simulate a new bike ride, make a simulation of a bike ride on a new track. For this, we have to take a deeper look into the model of bike riding, where on one side, the input is the power the bike rider gives into the bicycle, and on the outside, the output is the speed. So from speed to power, there are three main forces which come in, is the wind resistance we have to overcome, the rolling resistance and the pull of gravity, and some smaller ones like the acceleration from one speed to another or the mechanical losses. And because we have not that much time, I will rush a little bit on this. And we were able to come up with a formula for getting from the speed to the power, and which is pretty helpful if you have no measurement tool on your bike for getting the used power, but you can easily collect the speed. So for analysis the previous tracks, this will help us a lot. And on the other side, from power to speed, we will use later on to simulate a bike ride on new tracks, because it's the same equation just solved for the velocity. So we can put in account that the different grades of the roads, and we're able to play a lot with this formula.
I think you have
so,
to evaluate that.
This is how we collected the data on the previous tracks. The bicycle computer on the bike is collecting the data during the ride and later uploaded to the Strava, a website which is like Facebook for sports, where a lot of people are uploading their data, and we can download it pretty easily and import it to Mathematica through the provided API. There are two different kinds of data files. The activity data file, which is like an overview of a tour of an activity, which has the total distance, the total moving time, as well as a rough map of the tour which was done, which is compressed, but after we can decode it, we can show it with the geographics command. So in this example, this is the tour which was done. But for further analytics, we want to have this second type of data file, which is for every tour, which is called stream. And it gives for every measured data point the timestamp, the distance, the velocity, and the grade of this certain point. And then we can plot it and see like the profile from, and we can see the profile of the tour which was done, the different speeds. And using our power function, we then can see how much power was put in the bicycle during the ride. And it's in this example, it is tour longer, around 150 kilometers. It was around 115. Yeah, there's some measurement mistakes, you see. So it goes sometimes up to 400 watt, but in the average 115. So now we wanted to see how good our function, our model for bike riding is to simulate for simulation. And for that, we assume that the power we put in is constant. And then we have to find out, to testimony our model, we're using the data of a lot of, like, in this example, 80 tours to find for every specific rate a specific velocity, which I plotted here. And then we fit a function for it to lose all the noise. Because you can see if sometimes you stop, sometimes you brake, and so much mistakes. But it's pretty good. And if we use our speed function by the crate and plot it to this as well, then
it's not defined. It won't work.
Wait.
We didn't evaluate it. Doesn't help.
So it worked before. You can see that it's pretty close, that our function is pretty close to the fitted function. And we can play a little bit with the constant parameters, like the power you put in, or the height of the biker, or the temperature. And in the end, it's missing as well.
Let me fix it.
So and if you go and download our notebook, you will see that we can simulate our bike rider. Speed function is not. Then you can see that we can simulate pretty well with our speed function how the bike rider will drive compared to how he actually drove on the tracks we did.
Okay, so
come to conclusion.
Yeah. Okay. We have hoped to show you how simulated our model compares to the real ride on the profile between Cillian and Hamagor, the area we're looking at. And well, we find that when we are optimistic, we get some kind of fit. It does work, but this stupid rider sleeps in between. So you see it's really close until he goes to sleep. Then he's lagging it about the period he slept. So that's the reason we have, so that's in the data, and that's correct data, but we have to do more data cleaning, more trying to control for more variables so far. And what's the next thing we want to do is, what we really liked is the amount of data we have in OpenStreetMap. Surfaces, we can measure the angle of curves. So if we come to a curve, we can really see what kind of, if we have to break down or not, and there's plenty of data, and it's accessible. The huge sites makes it more problematic, but there's an interface where we can, for example, open Overpass API, which we mentioned shortly, where you can really ask for details on certain things. And with the there's a Osmanium C++ library, which allows you to work with the OpenStreetMap data in detail and make, that's really powerful. So we want to use more data because we get fascinated in what about the amount of data we have available and what we can do with that. And we have to work more because in our model at the moment, we do not really take care that we might go down a hill and then go in the flat. And that's the reason we have, for example, see these high values in the on the flat area, because we came down a hill. So we do have highly autocorrelation in our data. We didn't account for that either. So there's a lot of things we have to further work with the data, and that's what we plan to do in this environment. Thank you very much.